Today we're covering the last bit of 116, that is computing as experiment and spectral methods, which is spectral application, one of the two. First question, we have the matrix of an undirected graph having 10 nodes has a dominant eigenvalue, lambda 1, of 4, and the smallest eigenvalue, lambda 10, of -3. What is the minimum number of distinct colors required properly to color the nodes of this graph? That is, that no two nodes joined by an edge are given the same color. For this, there's two handy equations we can use. If we have the dominant and smallest eigenvalues, we can say that, where's the pen? There it is. There. That the, at most, maybe not so thick. At most, the number of colors is the dominant eigenvalue, plus 1, and at least it is 1 minus the dominant eigenvalue over the smallest eigenvalue, in this case 10. So let's just say n if you're doing generally. So we're looking for, what is this, minimum. We're trying to find the minimum. So this is just 1 minus, 1 minus the biggest, which is 4 over -3. 4 over -3 is 2.3 recurring. Because we're doing minimum, we want to round up, which takes us to 3, and our answer is 3. Okay, a 5-node undirected graph is described by the adjacency matrix G, with G equaling that. Which of the following is an eigenvalue of G? We can calculate this using Mathportal. If we put this graph into Mathportal, we'll be able to see up. We want to go here. We want to go into, where is it? Datas and matrices. We want to go into matrix calculator, I think. Eigenvalues and eigenvectors. We want a 5 by 5. So bush, and put the numbers in. 0, 1, 0, 1, 0. 1, 0, 1, 0, 0. 0, 1, 0, 1, 1. 1, 0, 1, 0, 0. There. Then we want to say find eigenvalues and eigenvectors. And we want to find the one which matches what we were given, and looking between the two, we can see that none of those are the really complex stuff, and it's just this one, 0. So this one is that one. Okay, another undirected graph. It's now with 12 nodes. It has an adjacency matrix whose dominant eigenvalue is 3.25. What is the maximum number of distinct colors? Before it was minimum, now it's maximum. This is doing that first one, which is the dominant eigenvalue plus 1, which is 4.25. And then we want to round down. Double check. Yes, we want to round down, so doing maximum, which takes us to 4. So 3.25 plus 1 equals 4.25. Rounded down equals 4. Okay, 10 people are chosen from a population of 1,000 to rate, given a numerical score of 100 in new car food. The reported scores are that which of the values below matches that of the Bessel corrected standard deviation in this example, and round to the nearest whole number. So this one, I believe I already had it open, but you can find it using the PDF that Paul gave us. But it's this one. If you go onto the modules page, you can download this towards the bottom, I think. And then we want this one. I've already got it open here, I think. Wait, do I? Oh no, I've got to open it. Well, I'll open it now then. It's this one. I believe standard Bessel corrected translation. Choose sample option for Bessel correction. So we want sample, and our numbers are 50, 12, 18, 80, 35, 62, 42, 20, 91, 62. Which I haven't missed anything. Yep. Okay, we'll compute the sample of that. Our standard deviation is 26.7. We want to be rounding that to nearest, which is 27. Go back to this. 27 is here. We want this one. Okay, an n by n matrix A containing only 0 and 1 entries is such that it's an eigenvalue which does not belong to the set of real numbers. Which of the following statements most accurately describes this behavior? This is one I got right without fully. Okay. So it's not singular. I don't think we can determine just from this if it's singular. Singularity based on determinant. If you find the determinant of a matrix, then if it's 0, it's singular. I don't think we can determine that from this. So the one of these which is most accurate or most precise, which is I think what Paul meant, is the I didn't put down. It was this one, a directed graph. The reason for this is that having a non-real eigenvalue, well, you cannot have non-real eigenvalues in undirected graphs. It doesn't work just the way they do. Because they're symmetrical, when you try to find the eigenvalues, they'll all be real. And honestly, I couldn't find anything else on why I couldn't have this and why I couldn't have this. So if you're able to find it, great, point it to me and I'll do a follow-up point somewhere saying why I couldn't find anything on why it couldn't have a dominant eigenvalue and why it has no eigenvalues as long as it's set of real numbers. Perhaps I'm missing something in the question that points to that. But for that one, it ends up being this one, and I think that's simply because it's the most precise and it can't be undirected because that would be a symmetrical graph. All undirected matrices are, all undirected graphs in adjacency matrix form are. So that. Okay, page rank. Okay, so the way that we want to find the row, apologies for the thing, clicked by accident before taking the screenshot. We want to find the row of C in the PageRank matrix used by Google search engine. We calculate this like so. For every outward link, or for every link into a node, you will get a proportion of the sender's score. So each sender will send 1 out in total, and that'll be evenly distributed between all of them. So if a single node passes to 2, each of those 2 will get a half. If it's to 3, each will get a third. In other words, it's 1 over the number of nodes a particular node is outwardly linked to. Example being, we have A is pointed by pages C, D, F. So C points to A. C also points to D and E. So A, D, and E will get a third from C. As in total, that'll be 1. We want to find the following describes the paper for C. So we want to find the score for C. So we need to find. And also you'll link it up in a sequence where each of these is linked to by what's the word I'm looking for? Each of these corresponds to one of the pages. So there are, I think, 6. There are 6 pages, so this is 6 long. A, B, C, D, E, F. We have with C. A and D point to C, so that's where its score comes from. A points to 1, 2, 3 things, so it gets a third from A. So A gives a third. Then D gives to A and C, so it gives it a half because it only points to 2. So that means that we want one of these where the A corresponds to a third. That's this one, or this one. and where the D is a half. That's the first one, so A, B, C, D. No, A, B, C, this one. That's this one that we're going for. This one doesn't have anything on D. This one has a third on. Actually, this one has nothing on D either. So it's this one that we're looking for. Oh god, this one. So yeah, this one's a mess. In the 116 channel there should be, I think it was Barney who said it. I can't remember. Someone contacted Paul about it, asking, because there's two different types of question times. You'll see this question: one where it's using RGB, and one where it's not. And for RGB, it's an extra because you have three matrices each representing one of the colors. Sometimes you won't, sometimes be in grayscale, sometimes it will be in a single. All the things will be in one unit. It's a pain. For this one, there's no mention of RGB, so I believe the solution is ignore RGB exists. Just there is one matrix for each of the three encodings, so we don't have three pair. So for this one, the idea is I just get this up on my notes. There we go. For the original matrix, we have a space consumption of h by w, the height versus the width, times the width. You can see here 1,000, 1,000, all of them. You get roughly 1 megabyte of space. I think exactly 1 megabyte of space, but roughly 1 millibyte of space. I might be wrong. I think that's how that works. We want to find a way where we can make an SVD encoding, which is using three new matrices. One which is the original h by w, like height times width, another which is the width times width, and another which is the width times the width. We end up with something like one which is h times w, one which is w times w, and then another which is w times w. And the idea is we shrink this one a lot, and this one as well, down all the way to try and get this value to be below this. And the equation for that is, if k is the width of the middle one, it is k times the height plus k plus the width. And we want this to be less than height times the width. So we're trying to find this. And in fact, because we're trying not just to find less than the original, but also less than a quarter of the original, we need to find one of these. If these are our k values, so k is 130, k is 150, 100, 115, 75. We would find one of those, which, when put into this equation as k, gives a value which is less than or equal to a quarter of a megabyte. And you just put those numbers in the equation after finding a quarter of a megabyte, which is 250,000. So we put this in, for example, 130. So 130 times 1,000 plus, that's 100, plus 130 plus 1,000. That gives us 276,900. That's too big. Is more than the 250 we're looking for. So that it's not that one. We can go again. We know it's not going to be 150 because that's going to be even bigger. Next one down is 115. So we try 115. We get 243,225. This is less than the 250,000. And because we also want maximizes the quality, we want the one of these which is k as the largest, because that's when we're throwing away the least data. This is a lossy compression method. So it's this one. This one and this one would also meet the criteria for less than a quarter, but would be throwing away more data than required. Next up. Okay, we have an n by n matrix A, which has an inverse whose dominant eigenvalue is 5. What is the unique smallest eigenvalue? Again, accidentally clicked it before doing it. Okay, so the way you do this is that when inversing a matrix, all of its eigenvalues are also inversed. So if for example, if A1 was inversed, it has a dominant eigenvalue of lambda 1, then this eigenvalue will be inverse. So it'll be 1 over 5. 1 over 5 is 0.2. And because it's dominant, we know it is the biggest and unique. To be dominant, you have to be the biggest eigenvalue and also be unique. The only eigenvalue of that value. Because you can have multiple eigenvalues all of the same value. So since we know this is the biggest unique, if we inverse it, we've got the smallest unique. So the inverse of this, which is what the original matrix will have, is 0.2. So we have 0.2. Big one here. Which, if any, of the three matrices P, Q, and R below is /R singular? The way you do this is by finding each of their determinants. If the determinant equals 0, it is singular. Which it will. Okay, it was Mathball that has this. Metric calculator. Go down a bit. We want to find the determinant of the 4x4s. I'm gonna refresh. I don't know if this will screw it if I don't refresh it. Or go back and refresh. There we go. 4x4. 4x4. Okay, first one is 0222 2022 3033 and 2220. We want to find the determinant. And we get 0, so we know P is singular. We go to the next one. It is 3330 0333 3033 3303. Find the determinant. This one is 243, not singular. And next one, 0, 1, that's not 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, and then 1. Find the determinant of 3. Oh, that should. Yeah. Find the determinant of 1. So all again, not singular. The only singular is the first one, which is P. So this one is just P. Okay, the characteristic polynomial of a matrix is found to be that. What are the matrix dimensions? So for this, we're going to need to expand and simplify this factorized polynomial into its full form. So again, this one, we want polynomial calculators, we want expand and simplify, and then we want to copy it over. We have x squared minus 2, and then x minus 3 squared. Oops. X minus 3 squared. And then, oh, that's shouting at me. There we go. Oh, because there's nothing in here. It's shouting because of that. X cubed minus 1. Which is right. X squared minus 2. X minus 3 squared. X cubed minus 1. Yes. So we're going to simplify this. And we get this. And then, from a characteristic polynomial, you can know that the dimensions of the original matrix, I think, believing that is a square matrix, but I'm not certain, corresponds to the degree of the polynomial. Degree being the largest x with non-zero coefficient, a coefficient of 1, so 7. So here we know that the answer is 7. In fact, I'll just okay. A slot machine game involves a player paying £1 to try guess which of the 7 distinct letters from A to G will appear on a screen. If the player guesses correctly, they receive £5. A player is prepared to gamble 200 in order to make a profit of 800. A total win of 100, including the investment of up to 200. Which of the statements below is correct? Okay. This one, I might be missing one of the videos here, because this one just seems probability, and I don't remember there being a thing in that. So potentially you could find expectation and stuff and see what it is. Another way you should look at it. There, you know from this, presuming a fair chance, even distribution, that there is a 1 in 7 chance of winning each time. And there are 200 attempts. So you can just multiply those two together. Which gives 28. Yes, 28 and a bit. 28 and a half approximately. So 28 and a half wins. So you'd expect to doing this, you would win roughly 28 times. With that, with those 28 wins, each of those would make a profit of 4. So multiply that 24 by 4, by 28 by 4, and you will get, that is not the right number. There we go, 114. So you would expect after playing 200 times to have received 114 back, and to have spent 200. So after those 200 times, you would then have 114 extra goes, and you can do this again. Multiply that number by a seventh, and you get another how many times you would expect to win. Do that, and it's going to be going towards 0. Every single time you continue, you're getting closer and closer to 0. So it is not very likely that the player will ever achieve it, because to achieve it, they have to win every single time after the 200. So after 200 plays, there is not a probability of more than a half that they will have made their goal. In fact, very, very small chance of that happening. And equally, there is not a probability of more than a half that they will have their money left. Because, as we've shown, there is a probability that they will have won 28 times, so they'll have money from that left. So it's neither of these. Another after 200 plays, very likely the player has between 180. We've shown that they will have 114, approximately. So it will not be that. So it's one of these two. So after some finite number of plays, it is very likely that the player will have achieved the goal of making 100. We've just shown that if we do this again, 114 times that, 114 times 1 over 7, or divided by 7, is 20. So that one goes even lower again, roughly is 20 and a half. Times that one by 4, now you have 82. So now we've gone from 200 to 140 to 82. This is clearly tending towards 0. So as they continue on, each time they're making less and less money, they're losing money overall, they're tending towards 0 and losing all their money. So it is not very likely that after some finite number of plays, the player will achieve the goal of making 100, because they're losing money on average. So then the only one that lives is this one. After some finite number of plays, it is very likely that the player will have their money left. If they continue going, they're going to lose their money. They're not making money. I'm honestly not sure what the way Paul wanted us to do. I don't think the way I did it was correct, but it also gives you the right answer. Okay, an experiment reports that the following set of results governing x, which is the number of hours climbed spent rising on an exam, and y, file mark achieved. All we care about is the gradient to the nearest whole number of the best fit line function for this data. This data, not these data. Data is not plural. It is, but these data just sounds horrible. Okay, for this one, we need to find the best fit line function. If we go here, I believe, yes. We go here. We go to statistics and probability, and then correlation and regression, I believe. Let me just double check my notes. Yes. I want the equation of the regression line. I want to use this. And then we want to put the numbers in. So it is 0.25, 0.5, 1, 1.25, 1.5, 1.75, 2.5. And then the this is 10, 25, 35, 45, 52, 60, 75, and 90. We want to compute this. What did I do wrong? I didn't actually press enter. 75, 90. 10, 25, 35, 45, 32, 60, 75, 90. There we go. Compute. We have this, and the equation of the line is this. Mx plus c. We want the m, the gradient, which is 34.4. That will be rounded down to the nearest whole number. So 34. Where is this? There it is. So this one is 34. And again, I'll just... That was the wrong set keys. Okay. A sample dataset is reported as giving results those. Using an unbiased distribution, what is the expected outcome? For this unbiased distribution, that means equal chance of getting all of them. So the shortcut is find the mean. Add them all up, divide by the number. So 17 plus 45 plus 21 plus 327. Divide that by the number of them, which is 10, is 32.7. We want to be round that to the nearest whole number. So that would be 33. So the mean equals 32.7. Round that up is 33. Here's this one. We have this data set. We want to find. So okay, this is a biased distribution. We want to sample all this and find it based on the probability given by that b of x. I'm pointing at the screen. I don't know why. A company wishes to download. So they're trying to cheat and make it look like they're doing better than they are using this function of probability. For this, we're going over back to this one. We want a probability distribution. Yes, it is. Okay, so we will put those values in. So it's 12, 10, 17. And there's a way to do this manually. I forget the equation, so I'm doing it this way. Put in 111. 73, 45, 62, long one. 10, 95, and 20. And the probabilities, so it is, if it's less than or equal to 20, it is 1 over 40. 1 over 40, I've skipped 10. 1 over 40. 1 over 40, it's less than or equal to 20, so this counts this. Okay, next one, if it is between 45 and 62, inclusive, it is 1 over 20. So 1 over 20, 1 over 20, 1 over 20. Okay, and otherwise it is 7 over 30. There we go. Then we want to find the expectation, the mean, of these values. So calculate that. We get out, and we get it is 4081 over 60. 4081 over 60 is 68. There we go, and if you convert that over, it's 68.01, so it is the nearest whole number, 68. Next one. Which of the following is an eigenvector of the matrix below for the eigenvalue 1? For this, we just want to stick that in an eigenvalue calculator and find which vector corresponds to 1. Over here, vector matrices, matrix calculator, eigenvalues and eigenvectors. There it is. It is a 3x3. So push to there, push to there. 0.25, 0, oops, 0 0.5, 0 0.25, 0 0.5, 0, 0 0.75, 0 0.375, 0 0.5, and 0. We want to find the eigenvalues and eigenvectors. We'll go through, and the one that corresponds to 1 is this one. 1, 5 quarters, 1. Come here. That goes there. There we go. 1, 5 quarters, 1. That is this one. And that's the one. And I think that's the last question. Yes, it was. Yes, what Joe said is true. If you want to form it as a inequality, rather than putting all the numbers in, you can just put an inequality solver like Wolfram Alpha, and it will tell you what the optimal is, and you can just round that to the at 118 to guess, so you can put that down to 115. Because you want to be going one that goes is the closest to it, but not going over. Okay, that's that. So if there's any questions, put them in. Otherwise, done for today. And good luck on the exam.
Thank you. Thank you. Hi, everyone. Was everyone using